Last.
All right, everyone. Welcome to Geometry of Data. We'll be studying about shape spaces and shape manifolds today. So before we start, let me share my screen for the online view. All right. Okay, so let's just start with what a shape is. Like, what do we understand by a shape? Any general ideas? What would you describe as a shape of an object?
The pattern which the outer boundary of any object forms.
Yeah, that makes sense. Anything else? So essentially, what we want to define a shape as is a unique boundary or a set of points that can be uniquely identified as one specific shape across three different types of transformations. The first transformation is location, irrespective of where the object is located. It's the same shape as long as everything else aligns, irrespective of whether it's translated across the screen or not. Like, irrespective of where this fish is present, it's the same shape as the other fish, irrespective of where it is. So that's the first invariance that we want. The second invariance is irrespective of how you rotate the shape should be the same. Like, the shape of the object is independent of rotation, which means, like, for example, if you have an ellipse like this, and the same ellipse standing on its head, like with the same equation, like literally the same ellipse, these two are still considered as the same shape, right? Because the shape of an object is independent of the rotation at which you present the object. The third invariance that we want is to size. So, for example, if you have like a small circle and a large circle, essentially these two shapes are also the same shape. So overall, we just want our shape to be invariant to location, which is the position in space, the rotation, which is the orientation of the object, and the scale, which is the size of the object. So a shape is just understood as the appearance of an object, which is invariant to these three properties, which is location, rotation, and scale, right? But how do we then define shape? Like, for example, even a fish like that needs to be represented mathematically or in some rotation to actually compare it to other shapes, right? So how do we do that? So there are different ways of geometric definition and descriptions of shapes. Yeah. So let's look at some geometric descriptions of shapes, right? The first one is just landmark identification, which means that, let's say you have two different shapes and you have specific landmarks on those shapes, like for example, point A. And this point A directly corresponds to another point on another shape, right? This point A. And then you have a specific number of landmarks across the shape, covering the outline of the shape. And you have landmarks on this shape as well, covering the outline of the shape. Once you have that, you can sort of compare these landmarks against each other as long as they are aligned to sort of do some computation between these shapes, right? Like sort of identify if this is smaller or bigger, if they are the same shape or not, how far away these shapes are. That is the first way of doing it, is by landmarking these points and sort of defining a shape based on the key points that it's made up of. So for example, like this. So in a case where, let's say you are looking at skull images, we would know that all skulls, irrespective of who it belongs to, will have the same landmark locations at different parts of the skull, right? So if you label them as such, and you have two different skulls, and the points sort of align with respect to meaning of what the point is, like where the landmark is in the skull itself, you can compare those two skulls based only on the landmarks. Right? So it is a uniquely identified point. A landmark itself is a uniquely identified point on a shape that can be used across different shapes to sort of compare them and see if they sort of align or not. And yeah, so this landmark is just, it should summarize the overall geometrical information in the shape using this location. So there are different sort of applications of this. As you see, it's used in biology a lot. It's also used in evolutionary biology, where you have different sort of skulls of different species. Through evolution, you have fossils, and you sort of compare how these transformed into each other by identifying the landmarks on those images. Right? All right. Landmark correspondence also is in itself a sort of an open problem, where if you, let's say, you must have heard of key point detection as a problem in machine learning these days, where, let's say, in an image, you have a person over here and a different person with his arms raised on the other side, right? So to be able to compare these two body positions, what we want is that we want a certain number of key points to be identified on this on the body, so that you can compare these landmarks, right? So you have to sort of identify where the hand is, and that would become one landmark. Where the hand connects to the body, that would become one landmark. So things like that, like where you have to do key point detection, is also not a trivial problem, because in general real images, you will not always have these landmark correspondences. So to establish the correspondence itself is also an open problem. But once you sort of have established this correspondence, where you know each object in your data is sort of labeled correctly, where each landmark sort of corresponds with the landmark in another object, you can then use this landmark scheme to sort of compare these shapes. On the right, you will also see that if that shape is sort of represented in the Euclidean coordinate system, you can also represent the other shapes as a deformation or a transformation of that coordinate chart itself. It is, instead of sort of changing the shape or trying to identify how the shape modifies, you can also sort of find the deformations in the coordinate chart itself to sort of find the differences between the shape and sort of to compare them amongst themselves. Right? All right. So in other geometric representations, there are boundary models as well. Boundary models sort of focus on describing the shape of the object using the external boundary, like we saw for general shape spaces. Even landmark detection also sort of puts points on the boundary. So any kind of geometric representation of a shape where you use boundary points to identify like the overall shape is known as boundary models. Boundary models can also be sort of simulated using Bezier curves and other splines and other mathematical functions, which sort of represent a line which would be an enclosure of the shape instead of just key points. So instead of having these defined key points which are discrete, you can also have like a continuous boundary which is made up of splines or Fourier lines or Bezier curves or Fourier descriptors to sort of define a shape. right? So it's not necessary that on the boundary you always have these points. As long as you can sort of define the boundary using some mathematical functions, that also sort of works, right? Any questions so far? Okay. Similarly, you can have, we also have another geometric representation where instead of the continuous boundary of the object, you have like a medial axis, which sort of sort of represents the orientation or the position of the body. Like in human key point detection problem that we discussed, you don't really sort of segment the body out completely. You only sort of identify the landmarks and only come up with the key points that make up the body skeleton and are able to define the movement. So you would have like some points in the middle of the head that would identify where that landmark is. So instead of sort of modeling the entire body, you are able to model the position of the body only using key points on the body, right? Which would go through like the medial axis of the object itself. Right? And that is one of the interior models. All right. Now there are transformation models as well, like we saw in the previous example also. Yeah, go ahead.
I have a question about the fact that you mentioned that these representations are invariant of rotation, translation, and scaling.
Correct.
I can understand that how these are invariant to rotation and translation.
Mhm.
How are these representations invariant to scaling?
Yeah, so we want them to be invariant of these three things. So sort of eventually when we define the shape space, we will make mathematical constraints which will ensure that you can't have two shapes that have the same scale, sort of mathematically. But just as an intuition, you can imagine we don't want two different shapes of like two shapes which have literally the same shape, but just are of different sizes embedded at different points in our manifold, right? If you want a manifold where every shape is sort of independently represented on that manifold, so if you have like a smaller circle and a larger circle getting embedded at two different points, that's not a very useful representation of shapes. So what we want is that the shape space should be sort of invariant to these three things that we mentioned. How we do that will be using some mathematical constraints that we'll go through as we go towards the end, right? Okay, yeah, so transformation models. So transformation models, as we just briefly saw in the previous slide, is that let's say you have like a template fish like that in the coordinate chart, and there are other fishes that also sort of look similar, have the same body parts, but are different, slightly different in terms of shape of the fish, right? So instead of sort of modifying or transforming the fish itself, you can again sort of modify the coordinate system, like directly the coordinate system and sort of transform it in a way where it looks like a different species. So these are diagrams from this book, which is like 100 years old, these diagrams. But so you can sort of see that this idea is not very new. It's been in academia for a very long time. And these transformations, notice that are always defined with respect to another object, because the transformation changes the coordinate system of one shape to sort of conform to other shapes. So you always have to have like this relationship is always between two objects, right? All right. Okay, so now we get to shape spaces, right? So essentially what we want is that we want a space, a latent space or a manifold where every point in that space is a different shape, right? So overall, what we want is that, let's say this is your manifold, call it M. And a shape on this manifold is just represented as a point here. So let's say this point X is a shape, right? And there are some shapes that we have in the slides. So for example, if you can imagine one of the points to be a shape like that, I will just sort of, to make it simpler, make this shape a square, right? So every point on this, in the shape space should sort of represent a different shape. right? That's what a shape space is. So that each point is a shape and the whole space is made up of different shapes, right? And the two different shapes which have the same shape but are translated across or are rotated or scaled differently should be embedded at the same point. So all sizes of squares, irrespective of how big they are, how they are rotated, should all map to this point, right? So yeah, so for example, yeah, just to demonstrate that there are different shapes in the space, let's say this is Y, and we make it a circle, right? All right. In addition to this, we also want the shape space to have a metric structure, to have a metric structure, which means that you should be able to sort of identify the distance between these 2 points. And why would you want to do that is to be able to compare shapes. Like we want this shape space to have some meaning in a sense that, let's say this is a square and let's say you have like a slightly rounded square, right? So this rounded square should be closer to the square than it is to a circle, right? That you can see intuitively. So what we want is that the shape space should also have that kind of structure where similar shapes are sort of embedded close to each other, whereas very different shapes are far away from each other. And there is like a smooth mapping between one shape to another shape where these shapes deform into each other. And this is a continuous deformation from X to Y. The shape becomes goes from a square to become a circle. Right.
So when you say like a shape is a point on the manifold, do you mean that the shape is located at the points or?
Yeah, so the shape itself, the entire shape, is embedded as a point in the shape space. This manifold is only representing the shapes themselves, and the shapes are made up of multiple coordinates. So a shape could be any dimension. Let's say if it's a triangle, it's 6 dimensional, right? Because every coordinate has 2 dimensions. But even then, you should be able to sort of represent that whole triangle with 6 dimensions in a shape space as 1 point.
Like how is it that point is represented as a shape?
Yeah, so we'll go through the math in the next few slides. We'll start to see how that's happening. But essentially, what has happened is that and this can be any dimensional. So 1 point does not mean that it only has like 1 dimension. It's just a point in this high dimensional space where it can have any number of sort of dimensions in the vector. So to completely represent a shape as a point in this space. Yeah.
So will the cube and square both point to X? Or will cube be a different?
No, so cube is a different shape. So the shape needs to be, so cube is already 1 dimension extra, right? So we are only talking about close 2 dimensional space shapes here in this example. But if you could imagine there's a cube which sort of looks different than the shape across scale, translation, rotation, that would be embedded as a different point.
So this manifold M is for all shapes of 2 dimensions.
Yes, all closed shapes of 2 dimensions, like just in the example here, yeah. But you can make it any dimension, depending on what shapes you're looking for. All right. Any other questions? Okay. All right. Yeah. So so we want this Riemannian metric between the X and Y to be able to sort of have some meaning to the shape and be able to identify the differences in the distances and how close these shapes are. This metric is very important. All right, so now let's just look at some examples of shape spaces, right? 2 examples that we will one example that we'll go in detail is for the Kendall shape space. We'll look at how that is derived, how that is embedded, and the other example is just for your intuition purposes. So there are different types of shape spaces mathematically defined where this happens, where you can embed a shape as a point in that shape space and sort of use the distance metric to compare properties of the shapes. And there is another shape space called the space of diffeomorphisms. As you imagined in the previous example, where we saw that the coordinate system was being deformed to sort of get a different variations of the same shape. This is what is happening here. It's like an infinite dimensional Riemannian manifold where the shapes are sort of represented as the deformation of the coordinate chart itself. So there's a template shape that you would have as the basic template that is like the original coordinate system, and then you transform that space in various ways to sort of get different shapes in that space. So that whole space is also a Kendall shape. Oh, sorry, also a shape space. And the Kendall shape space will look at detail. Look in detail later. So yeah, so Kendall shape space is key point based. One more time, key point based. I mean, which is sort of built up of landmarks. So the outer body of the shapes is not defined using curves or lines. It's just discrete points, right? Like we saw in the Kendall landmark geometrical representation. So we will use that for the Kendall shape spaces as well. Right. So one more thing that we need to sort of get an intuition for in shape spaces is that if you move from the point X to point Y, let's say, right, along the metric, along the geodesic in this space, this shape should sort of smoothly transform into the other shape, right? So imagine that you are on this curve, and at this point you find the tangent to this curve, right? V. At this point, you find the tangent along this curve at point X. What should happen is that this whole shape should start deforming into that shape. And how will that happen? Is that, let's say this is the circle and this is your square. Every key point on this square should start moving so that this shape starts resembling a circle more and more. Right. So at the initial time step when the shape is just the circle, so imagine that this is your shape and this is the target shape, the circle. This point, can anyone guess what the velocity of that point would be on the corner? Anyone? Just a guess. Because this square needs to transform into the circle. So every point is moving from their original location to their final location, right? At different velocities, depending on where on this curve you are. So what will be the velocity of this point? At the edge? Yeah, 0, correct. Because all of these points are already at their correct locations on the landmark, right? You already have correspondence between these points. So even though you find some velocity to this curve, not all points on this curve are moving, right? Because you only need to smoothly transform from a square to a sphere. So this point will be moving the fastest because it's the further away, like the furthest away from its target location. The velocity at this point would be higher than the velocity at this point, which would be higher than the velocity at this point, and this point would be 0. Right? So the whole shape is sort of transforming. So here also you can see that at a point P, which is this shape, if you find the velocity along any curve, the shape would be deforming, but every point on that shape would be moving differently, depending on what that curve is and where you are sort of moving towards. Right? Okay. Any questions about this? No? All right. Okay, so next let's talk about shape equivalences, right? And we already sort of saw this a little bit before, but what we want is that we want like a mathematical definition to what it means for two shapes to be equivalent, right? We already sort of briefly mentioned that they should be invariant to scale and invariant to rotation and also invariant to translation. But what does that mean for like in math? So it essentially just means that if you have two shapes x1 and x2, what they should so shapes x1 and x2 are equivalent to each other if they are just translations, scalings, or rotation of the other shape. If x2 is just a rotated version of x, it's the same shape, so equivalent. This is what we have been sort of discussing so far. So essentially, what should happen is that x2 should be lambda times rotation times x1 plus y. V here is the translation. that you move x like x1 by this amount. R is the rotation matrix. So you have like a matrix that sort of rotates your object a little bit, and lambda is the scale factor. So if you want to scale the object a little bit, you can change the value of lambda. But x2 and x1 will always be equivalent because they are they follow this relationship, where x2 is just a rotation, scaling, and translation of x1, right? So this sort of equivalence in mathematical notation is denoted as a tilde sign. So if we want to say that x1 is equivalent to x2, what we do is just say that, right? This is an equivalence relationship between x and y, which means that they are equivalent to each other. Now imagine that we have all equivalent geometries as an equivalence class, right? So let me just define what an equivalence class is. Okay, so a box around x. So now you can see that there are multiple shapes that could be equivalent to the same shape, right? And we only want unique shapes in our space. We don't want multiplication. So what we want is that this represents an equivalence class, which means every shape that is equivalent to x is in this class. So all versions of x1, x2, x3, if they are the same shape, belong to this class, right? So this is mathematically defined as a shape y such that y is equivalent to x, right? So a class of all shapes that are equivalent to x is the equivalence class of x, right? So this is just the equivalence. Right? Now, what we want in our tensor shape space is that all of these shapes should be represented, right? So a set of all such equivalence classes is called a shape space. That's it, right? If you have this equivalence relationship where you are able to define one shape as an equivalent of any other shape, the space of all such equivalence classes, which means all possible shapes, is a shape space. So as long as you are able to represent all of these equivalence classes into the same shape space, then that is called a shape family, right? Make sense? Because all of these shapes are equivalent to each other, and all of these equivalence classes are different shapes. If you embed all of them on the same manifold, it becomes a shape manifold. All right. So let's concretely look at, oh yeah, so again, see, yeah, equivalence class is just x1 tilde x2. It's yeah, so there are three properties of this equivalence also that I sort of forgot to mention. It's that this relationship is reflexive, which means x1 will always be equivalent to itself, right? So any shape is always equivalent to its own shape. So yeah, so this means that this is reflexive. Another property is that it's symmetric, which means that if x1 is equivalent to x2, that implies that x2 is also equivalent to x. That's symmetric. And also it's transitive, that if one shape is equivalent to another shape, that shape is equivalent to another shape, the first shape is also equivalent to the third shape. That's just the three properties that we have, and then all these equivalence classes of the shape space. All right, so let's look at Kendall shape spaces specifically. All right, so there are very concrete steps to creating Kendall shape space based on the theory and the intuition that we have sort of discussed already. We want every point in the shape space to represent one point. We want a metric relationship between these two any two shapes, so that we can sort of identify how far away or how close they are. And there should be no duplications in the shape, like every shape should be unique, right? So to sort of do that, these are the 4 things that we have to do. The first thing is we define the object with key points. Like I mentioned, in Kendall shape spaces, we use the key point representation of the shape. So we find the boundary points on the shape and use the key points to sort of represent the shape. So we define the object with the k points, and this k stays fixed. So in this shape space, every shape needs to have the same number of points, right? So yeah, irrespective, you choose what the k is, and then you represent the shape in R2k. And why is that? Because every coordinate has to, every point has 2 coordinates, right? Like every landmark, every key point is 2-dimensional. So you represent it as a vector in R2k, right? For example, if it's a triangle, how many dimensions would it have? What will be k for dimension? 3. And it will be represented in R6, right? Because 2 points for each, right? Okay. Yeah, so let's look at quotient spaces a little bit before we sort of progress with defining the Kendall shape space. Let's look at quotient spaces very briefly. So quotient spaces are something that we need. And I'll go a little bit more in detail than the slide. So some things might not match, but you can sort of, it's the same idea. So what we need quotient spaces for being able to sort of define a projective space after this. But essentially what we do is that for n equal to 1, just imagine, like let's say for dimension n equal to 1, a projective space is P Pn of y on the real line is a set of 1-dimensional subspaces right. So if we're talking about a projective space, is a 1-dimensional subspace of Rn plus 1. So irrespective of what your dimensionality is, if you are in R3, a projective space would be in 1-dimensional field for n3 space, right? So essentially for n equal to 1, we imagine R2, right? If n equal to 1, then the shape, the dimensionality of the subspace is R2. In this case, the quotient topology is just defined as straight lines that go through the area, right? Because, oh, sorry. Yeah, so all of these points that you can see are sort of are the set that we'll be using for this topology, right? So every line is a unique line in the space, and any point on this line is sort of mapped to the same line, right? So it's a subspace in R2 where all of the points on this line are represented the same way, right? So it's just a space of the rotation of this line. So all of these lines will be uniquely represented, and every point on that line is just mapped to the same thing, right? So now that we have the set, so every sort of space needs to have a set and a topology over it, right? So we have a set. Now what we want is a quotient topology on it. So imagine that you have an x, t topological space. And we also have the equivalence relationship that we defined before, like this equivalence relationship where we can use that to to see if two objects in this space are equivalent or not, right? And the equivalence relationship again has the same three properties that we discussed: the transitive, reflexive, and symmetric property. So the equivalence class of X here again is defined as, and I'm using a small tilde here because the equivalence is across this operator. So this connotation, and this again is, as we just defined, is just an equivalence class of all y's that belong to X, such that y is equivalent to X. Right, so this is the equivalence relationship also that we have in this space. Let's also define a canonical projection. So what a canonical projection is that it's a function q that takes you from X to this quotient topology that we represent as X divided by tilde. Right? So this is the quotient topology that we're talking about now. Like a topology which only has these rays is not X directly, because X was our space that we started with. Yeah. And this is the subspace that we are now talking about, the quotient topology. So a function that can take points from X to that quotient topology is a canonical projection. Right? So what we'll do, we'll take X and a function and then find all equivalent points. Right? So essentially what you're doing is that you're just reducing all of the shapes into its equivalence class through the canonical projection. So irrespective of what the shape is, if it's equivalent to another shape, it will get reduced to its canonical form, which is the same shape. Right? Okay, so let's look at one concrete example just to make this clearer. It's a little hard to sort of wrap your head around, which is why let's look at one example that will make it slightly more clear. And then we can do questions. I think that will help as well. Okay, so now imagine the X shape that we are finding as a rectangle. So this is what your X looks like now, right? This space is X, right? And we are defining an equivalence class as a line in this space, right? Which means that every point which lies on this line is equivalent to every other point that is on that line, right? So this is the equivalence class. Depending on what your point is, you just find what the coordinate of that line is, and that becomes the equivalence class for that point. And every other point on that sort of line is equivalent to each other. We just want to show an equivalence relationship and how that works with a quotient topology like this, right? So now you can imagine that if I find a canonical projection for this space, what would it look like? Any guesses? Because we are sort of collapsing all of these equivalence classes, because all of these get sort of represented as the same point, this whole line. What would the sort of the quotient set look like?
A line.
Yeah, correct. So it'll just be a line where this dimension sort of somehow transformed and represented as this dimension, and all of these points will sort of get embedded at some point here. So this, let's say x1 will become x1, right? And this is equivalent to all the similar x1s, right? Any other, let's say this x1 prime is there, that will also get mapped to this. Yeah.
Why all the points on the vertical line are equivalent? Why
Yeah.
say the one on the horizontal are also?
Yeah, anything like this is like we are sort of only using this equivalence class to sort of demonstrate this principle. You can sort of define an equivalence class as anything. Like in the previous example, we defined the equivalence class as the as if the shapes are equal or not. So that is what we eventually use. Is you just need an equivalence relationship where the relationship sort of should identify which two shapes are equivalent to each other. So here we are just assuming that anything that lies on this line is equivalent to each other. So in that set, like in that scenario, this is what will happen.
So we just say that all the vertical and horizontal are both in one equivalent class.
Yes, in that case, this will then become the same mapping as before. Like it won't collapse anymore because every point will sort of be represented as a different point. Like for example, x1 and x2, based on what you're saying, would be x1 would be here and x2 would be here, right? Because you're saying that only points that sort of are at the same point are equivalent to each other, but that sort of doesn't really give you an equivalence relationship between two distinct points because you're already going from R2. So you need to define an equivalence relationship that sort of reduces that the size of your sort of relationships.
So basically, it's like all the points in one equivalent class are shifting into one point on the
manifold. Yeah. So essentially what we want is that on your manifold, all of the points that are equivalent to each other should be just one point, right? Like in tangent shape spaces, what we want is all of the equivalent shapes to be the same point. Here, what we are saying is that all of the points on the same line should be the same point, just to demonstrate how the math works. Right? Does that make sense? Okay. Yeah, so now we need to see if these are open sets or not. Like we use all of our previous structure that we had already defined for spaces like these. We want to see if this quotient set, this is what a quotient set is called, because right. So we find an open neighborhood around this point called U. What we want to show is that U is open when the equivalent map in this is also open, right? So let's take the U through this mapping, but in the backward direction. So here, when you do that, what you will find is that you'll find a band, which is Q inverse of U, right? Because if you take the Q transform for the point here, you'll go there. If you go back, it's Q inverse, right? Basically. And now you can already see that this Q inverse of U is a subset of X and is also open, right? Because if the boundaries are open, it will be open here as well because the map follows all the properties that we used for mapping functions in manifolds, right? So this is open. This sort of also implies that U is in X in the quotient topology of X, right? In the quotient space, which is represented as X divided by the theta, is also open, right? So we have this open criteria fulfilled, and Q inverse of U will have this topology T that we already have, like X had a topology T already, right? But the equivalent map here U will have a topology right? Which is the topology of the quotient. So there's a quotient space topology. Right? So this is just an abstract example. Let's look at one more, a little bit more concrete example, which will slightly make it clearer, but let's see. Okay. And this is a Mobius strip example. very common example used in topology, the movie strip. Right? Okay, so a Mobius strip, the x in this case is defined between 0 and 1, and the y eventually goes from -1 to 1. Right? So what we are defining is that this rectangle, like this, goes from, this is the horizontal axis, 0. This goes from 0 to 1, 0 to 1, and we have a closed interval, which means like this is closed. And this grows from like -1 to +1. Right? This makes sense? Okay, so this is a Mobius strip. But now, as you know, there's an equivalence relationship in Mobius strips as well. This point, if you sort of take this edge of the strip and connect it to this edge, whereas you take this edge and connect it to this edge, like this, that will sort of construct a Mobius strip, right? Does that make sense? Does everyone know what a Mobius strip is? Okay, so a Mobius strip is just a thin sort of a flat piece of paper. If you add a knot to the paper and sort of join the paper back, it becomes a Mobius strip where it has only one side. So if you start following the strip on one side and keep your finger on it, you will end up on the other side of the strip. Because, yeah, so the example that people mostly quote is that it looks like, it's a little hard to draw, but let me try. Right. So the idea is that if there is an ant, for example, an ant here, and it starts walking on the strip, what will happen is that it will go inside the strip while it's walking on the straight line and end up at the same point again, right? If it does two rotations. So that is what a Mobius strip is. Yeah, so you construct a Mobius strip by just joining this end to this end and joining this end to this end. So it sort of establishes an equivalence class, and we'll do that mathematically here. So the equivalence relationship here, let me just write it down. Here is that 0, 0, s is equivalent to 1, minus. Right? Does that make sense? Any point, if it's here, it's, let's say 0, s will be mapped to a point 1, minus. Right? Because you go, depending on how much further up from the origin you are, you go the same amount of length down from the origin. And that makes this Mobius strip, right? Yeah, so if you look at this construction, because this also has an equivalence relationship, and everything else sort of follows the same topological rules of Euclidean spaces that we saw before, this is also an example of a quotient topology. Because based on the equivalence relationship, different points are getting mapped to the same sort of same point based on what the equivalence is, right? Irrespective of whether you are here on the strip or there on the strip, they get mapped to the same point essentially, right? So that's what an equivalence relationship is. And if you introduce such an equivalence relationship in your topology, then sort of and with other conditions, you can sort of create a quotient topology. All right. So now let's move on very quickly. Yeah, so all right, so you can use now like going back to the slide, so you can use these quotient spaces to also remove scaling from a point in R2. How do you do that? Is that, let's say your equivalence relationship is defined. Yeah. So yeah, so what we want is that we want to remove scaling, right? So let's say we have an R2 space like this, right? And we have a point X here, right? If we define an equivalence class of X to be a vector that joins X to the origin, this is what the equivalence class of X will be, right? And by equivalence class, I mean that every point on this line segment should sort of have the same representation in your space. Irrespective of where you are on this line, it should have the same representation, which is the equivalence class, because we are considering all of these points to be equivalent to each other, right? And that sort of removes a notion of scaling from these points, because irrespective of how big or how large this line segment is, if you represent it as the equivalence class, which is sort of essentially just projecting it back to a unit circle, which is radius 1, irrespective of how large your line segment is, it will always be of length 1 and only be represented by the angle it makes with the axis. Right? So you sort of can imagine how this is removing the notion of size from these points, because everything is sort of getting projected to that. Yeah.
But in this case, then like the origin, wouldn't the origin be in all the equivalence class?
Yeah, and origin, what do you mean? Sorry, I didn't get it.
Because like it's like all the lines in all the points on one line is in equivalent class, right?
Yes.
So in this case, like origin is in each of the lines, right? So wouldn't that be?
Yeah, that makes sense.
I don't know if the origin was included.
Yeah, I don't think the origin is included. Let me, Professor. In this example, is the origin included in the, because that will keep getting projected to the same point. Yeah. So the origin is not included. So any other point will get projected back to a unit circle where its equivalent class is like this bracket X, and that is what you'll use. Irrespective of what the size of that line segment is, all of them gets projected back to this group. Right? Okay. Okay, so let's get back to constructing the Kendall shape space finally. All right. So again, consider the 4 steps. Again, the first step is to consider planar landmarks to be points in the complex plane, right? So there are 2 ways of embedding things as in Kendall shape spaces, and we'll look at both of them. The first one is through complex numbers and complex math, and this is that method. And the second one we'll look at as an like an alternative method which uses orthogonal percussive analysis, and we'll talk about that as well. So this one is using complex planes. So what you do is that you consider the planar landmarks, which is the key points in your shape, as points in complex plane. A complex plane, like we remember from like previous math, is just a 2D space with a real line and an imaginary line, right? So we'll review some complex math in the next slide, but that's what we want. Then the object is sort of represented in this k-dimensional complex space as k points, right? And then we remove translation from these points. And the way we remove translation is just that we subtract the mean, the centroid of the shapes from each of those shapes independently, right? So for example, let's say you have Z1, Z2, Z3, or 2Z, and what we do first is find centroid Z star. which is the Z star, the median shape of these points. Then we subtract Z star individually from each of these Z1 through Cn, right? To get a new representation Z hat, oh sorry, Z prime, which is essentially just Z1 minus Z star, Z2 minus Z star, and Zn minus Z. Right? Now we are claiming that Z prime has no, is centered around the centroid, right? Because all of the shapes are now sort of centered. Now what you would notice is that the sum of all of these individual components is zero, because we have sort of centered it around the mean, or sorry, the centroid of the shapes, right? So you will notice that Z1 through the n, like Z1 hat plus Z2 hat plus Z3 hat, dot dot dot, to Zn hat will be equal to 0, right? So we have sort of added a constraint to our representation of the data that we already have, like the Z1, Z2, Zn, right? And by adding this constraint, what we have made sure is that, for example, imagine a real coordinate system. And if you have this constraint where x1 plus y equal to 0, all of the solutions of that, x plus y equal to 0 is like this, but okay, x plus y equal to 0, all of the points will be constrained on this line, right? So you can imagine that we have also sort of constrained all of these points in a higher dimensional plane, which sort of follows this constraint, right? Because this is the coordinate systems, the sum of all the coordinates is 0. So there must be a higher dimensional plane in whatever dimension these points are embedded, where all of them lie across this plane, right? So we, in a sense, sort of intuitively have reduced 1 degree of freedom from this system, right? So just removing the translation will leave you with Ck minus 1 dimension. That is the sort of intuition behind that. Is that clear? All right. Now what we want is that we want to scale this, or sort of remove the scale and the rotation also from these objects, so that the objects are aligned irrespective of the shape size and the translation. All right. So let's just look at how do we do scaling and rotation in complex planes, right? So okay, so consider that this is the real line, this is the imaginary line. Any point x here is written z. Let's consider that the point is called z, right? So z here, as we know, is just r e to the power I phi, if this is the angle phi, right? Right. What we want is that we want to rotate this by an angle theta and also scale it up so that it is no longer at this point, right? We want to rotate this segment by another theta degrees and want it to be sort of projected to a length which is higher than mu, right? So how do we do this? So if you recall complex multiplication, if we multiply the z by a factor of s times e to the power I theta, what will happen is that you will get a new point z prime, which is equal to s times r times e to the power I theta plus phi, right? That here. right? It's just complex math. So this is just S E I theta times R E I phi, and that becomes that, right? So what we have essentially done is just by doing a complex multiplication between two numbers, we have scaled this vector z to z prime, where the length of the vector has increased, like sort of increased by a factor of s, right? It was r before, and now it's s times r, and also the angle of the segment has changed by theta degrees. So essentially what is happening is that every time you multiply by a factor like this serves as the scaling parameter. And then this is the rotation. Right? All right. So now we have seen that multiplying by a constant omega, which is just this, let's not omega, it's w, something like this. If it's any omega in the complex plane, will sort of rotate and scale your original vector, right? So now what we want is that an equivalence class, which is sort of neutral to all of these rotations and scales, because we've already removed scaling, as you recall. We've already removed translation. As you recall, what we want to now remove is that scaling and rotation. So we define an equivalence class Z, which is just a scaling by a constant factor. Okay, let me rewrite that because there's like a typo in that. Sorry. Yeah, so the shape of Z can now be reduced to an equivalence class Z, where it is a set of WZ1 from WZ2 Cn for every element of complex minus the original. Right? Yeah, so the difference there is that note that we don't really want 0 as the scaling and the rotation values, because that will sort of again sort of point you back to the original, because if you multiply by 0 then the scaling reduces. So instead of that, for every rotation and scaling, this should be an equivalent class, right? Like all your points, so irrespective of what the omega is, should belong to the same equivalence class. Yep. All right, and this is the second method of doing the same thing. Yeah, but here we will use matrices math, matrix rotation and matrix math instead of the complex math. Yeah, so let's just look at this also. Okay, so here what we do is that we first represent the shape as a D cross K matrix, where K again, as you recall, is the number of key points. And each point is D-dimensional. So D-dimensional points. So that is the first step, is represent your data like this. Step 2 is then again remove translation. To remove translation, subtract the row means from each row. So once you subtract the mean of each dimension from that dimension, you will then be able to remove the translation. Like we saw in the complex case, the same thing. But because it's sort of represented as a matrix, D cross K or K cross D, doesn't matter. What you have to do is from each dimension, you have to subtract the mean of that dimension, and that will give you the same matrix, but the translation would be removed. So everything would be around the origin, right? And then we want to remove scale, and to remove scale, we just divide it by the Frobenius norm, and that would sort of remove the scale, and then essentially what we want to do. Okay, so orthogonal progressivities analysis. So let me give you like a background story that professor always tells us in this class. So Procrustes, the name Procrustes comes from a Greek myth where there was this inn, like a hotel, which Procrustes ran, where anyone who came to the inn, he was given a bed, but the bed was always the same size, right? So if the person who came to the inn was shorter than the bed, Procrustes would then stretch him, like stretch the person to fit the bed. Or if the person was longer than the bed, he would cut off their arms and legs and sort of make them fit in the bed. Right? That's the myth. And essentially, we sort of use that in math because what we want is that we want two shapes to be aligned as such that they are closest to sort of each other. You know, like you remove rotation, scale, and everything so that the shapes are aligned, like Procrustes aligned the people with the bed. Right? So that is how the name is. Yeah, that's how this gets its name. All right, so what we want to do here is that let's say there are two objects. So what you do is that you do this with two objects because this Procrustes analysis is always with respect to another object because you are removing rotation with respect to another object. So you're aligning two shapes. So you do the same process with two shapes A and B. And then what we want is that we essentially want a value for the rotation so that such that when we rotate A, because we've already removed scale and translation, the previous steps, as we saw. So you remove scale and translation. All we need to now sort of do is sort of align the rotation so that both the objects are aligned to each other. So what we want is an ideal rotation matrix R star, which would reduce this value. Right? And that is sort of slightly clear to see because if you imagine that RA is just B, this will sort of be minimized, right? So what we want is that such find rotation matrix R such that this value is the lowest it can get. And you do that by just performing a single SVD on this system equation, and you find yeah, one second. Yes, and then you perform SVD, and eventually, when you do that, you will find R star to be equal to U V transpose after the singular value decomposition. And note that this rotation matrix needs to have a determinant of 1. So let me give you some properties of the rotation matrix. So the rotation matrix essentially should be a D by D matrix, right? Because sort of rotating the whole thing. And also our transpose should be our transpose R equal to I, which means that R is equal to its transpose. And also from these properties, you will need to have the determinant of R equal to 1. Right? But when you do this SVD analysis, there is no guarantee that R star will come out having a determinant equal to 1. It might have any determinant equal to -1 as well. In which case, you can just sort of swap columns or do a basic flipping to make sure that the determinant is equal to 1, and then that will be the solution to this equation. Right? Because we need to make sure that the determinant is equal to 1 because the rotation matrix properties sort of dictate that. Right? Any questions so far? Anything? Alright, so let me just give you a very quick sort of example for Kendall shape spaces for triangles, right? So for imagine that you have triangles as your data. The triangle data, as we sort of pointed out, is in 6 dimensions. So it's essentially sort of embedded as an R6 data, right? And then what we do is that the first step is to remove translation. So you remove translation, and that will give you how many fewer dimensions? In this case, actually it removes 2 dimensions because each point is sort of 2 dimensions. So it reduces it from R6 to R2 times 3 minus 1, right? So it'll go to R4. Right, so in general, this is like, let's say, imagine if this is R2K, this will reduce by 2, so R2K minus 1. And, oh, sorry. Right, and we saw that in the complex plane, only 1 dimension was reducing because the complex plane itself, every dimension is made up of 2 dimensions. So you would automatically, instead of saying that it's R2K, you will say this is C1K. If this was a complex plane, right? So if you remove translation from a complex plane, you reduce 1 dimension, but here, because it's a real, you reduce 2 degrees of freedom, right? So you go to R4, and then when you remove scaling, what happens is that you suddenly switch from being in the real plane to being on an FT manifold. And S3 is just a sphere manifold in a 3-dimensional sphere manifold embedded in 4 dimensions. So it's still embedded in R4, if you imagine, but everything is sort of collapsed to a sphere because we are removing scaling. If you recall, when we're removing scaling in 2 dimensions, everything was collapsing to the sphere. So just like that, in a higher dimensional space, everything will collapse to an S3 sphere for triangle, right? And for a general case, this would be S2K minus 3. Right? 2K minus 3 is still sort of embedded in 2K minus 2 real dimensions, which is equal to 2K minus 2 here, right? So it's the same thing, it's just because of reduction, removal of scaling, everything is sort of collapsed towards here. And then when you finally remove rotation from this, so yeah, it's remove scaling, right? So remove rotation. What you will finally get is an S2 space, which is what the Kendall shape space is a S2 sphere. For the case of triangles only, this becomes a S2 space. But for the general case, this essentially reduces to a complex projective space of K minus 2 dimensions. And we'll look a little bit more in detail about what this is in the next class, because it'll be too much to sort of cover now. But just remember that you go from S2 to S3 to a complex projective space, which in the case of a triangle is just an S2 sphere. Right? Yeah. So let's just end there today. Any questions?
Was the determinant equal to one? What would happen if it is -1?
So -1 is just,
Determinant -1 for this question?
yeah,
Yeah, then you get a flip. Like if I just negate the x-axis, you mirror across the y-axis, if you will. Right, that's a determinant -1, but still orthogonal.
yeah, but it would flip your shape, which we do not want. We want to rotate the shape so that it maintains its orientation, but does not get flipped. Because flipping the shape will automatically sort of give you another problem. This would be a different shape.
Yeah, like find that, yeah.
Yeah, left hand flip with right hand, so something like that would happen. Yeah. Any other questions? Alright, see you in next class.